Hello, fellow. My name is James Owusu-Appiah, and I believe in innovation and doing things differently. This video has been prepared for you to guide you through some well-known concepts that will aid your studies and preparations towards exam. Due to COVID, we cannot meet in person to discuss, so I hope this video finds you well and helps you achieve excellence. Thank you.
Hi everyone, welcome to the Micro PE tutorial series. The aim of this series is to help you get started with your Micro PE design project. So I will basically be creating a template that you can use to get started quickly. So the tutorial will be in 3 parts. In part 1, I will give you an overview of microprocessor and microcontrollers and the various components that make up these systems. Then we will move on to part 2 where we will design our data path. That is, we are going to arrange the various components and then create a connection between them. So that is just basically how what designing a data path is. Now from there, then we'll go to part 3. So part 3 of the video will focus on creating our instructions and then designing the control unit to execute the instructions. So basically that's how it's going to be like. So without much delay, let's get started with part 1. Now let's see. So a microprocessor, so in the simplest form, this is what a microprocessor is. It's an integrated circuit that consists of these things, right? So it has, within a microprocessor, there are what registers, and then it has a control unit or a control unit, and then it has a arithmetic sorry about that. It has an arithmetic and then logical and then logic unit, the ALU, right? So this is responsible for doing arithmetic operations and then logical operations, right? And so this is just basically what a microprocessor is made of. And then, so with that in mind, it has it has several pins, so that a lot of pins. So these are like input and output pin, or a lot of these pins, and the purpose is for them to interface with external component like RAM, memory, and then maybe input and output port or something. So these are the pins. So a microprocessor has a lot of pins. So let's take a typical microprocessor, for instance, so that you can kind of understand it better. So I have some few images as well. Let me check that. So let's take the Intel Core i7, which is a microprocessor. This is a microprocessor. So what it means is that, so in the simplest term, what it means is that the Intel Core i7, so the Intel Core i7, this basically has a, so this basically is made of, it has series of registers. So within this Intel Core i7, right, there are series of registers inside, and then it has a control unit, and then it has an ALU for. So basically that's what I mean in a more basic form. That's what will be in your i7 or something, so Core i7. And then if you see here, so these are the pins I'm talking about. You see, these are a lot of pins, and the purpose of these pins is so that it can be able to interface with external memory, that is external RAM, right, and then other memories too, and then also to interface with input and output devices like IO port or something. So these are, so that's how a microprocessor is like. It has a registers, made of registers, control units, and then ALU, and then it has a lot of pins to be able to interface with the external module like the RAM, and then input and output port. So that is that. So now this is always confused. A microprocessor is always confused with a microcontroller. So let's see what a microcontroller actually is, so that you can know the difference between these two, because they are actually not the same thing. There is a clear difference between them. So let's see what they are now. So I have here side by side. This is okay. So this is how a microcontroller is, and then this is a microprocessor on this side. Now let's see the microcontroller, right? It has it has a room, it has a RAM, it has an IO port, right? And then it has a microprocessor inside. So you see the whole nature of it, right? So a microprocessor has no room, has no, like, it has no internal room, it has no internal RAM, and then it doesn't have this an IO port inside it. Like, it has no interface, like internal interface for this IO port. So it rely on external ones to be able to work. So that is it. So this is a microcontroller. This is how it's like. Then this is a microprocessor. So you can see a microcontroller basically is a microprocessor with these other additional stuff inside it. So let's see a typical microcontroller. Yeah. So let's see a typical microcontroller. I'm sure the one that most of you guys will be familiar with. And let's see the ATmaker 328. So this is a microcontroller. The ATmaker or the ATmaker 328 is a microcontroller, right? So what it means is that it has a control unit, it has an ALU, it has registers, it has RAM, it has room, there's a flash memory or the instruction memory for storing instructions. So it has all these things. It also have internal interfaces for this, for input and output stuff. So this ATmega or ATmega 328 is a microcontroller, whereas the Intel Core i7, Core i5, all those iCVs and stuff, and then even the AMD Ryzen and these things, they are all what microprocessor, right? So they basically has control units, ALU, and then registers. That's basically what is contained within them. So with that out of the way, now that we know the difference between the two, so let's see. So now that we know what a microprocessor is, what it is about. Now let's see what we'll be doing here. So we are actually going to be building or creating a template or creating a microprocessor, not a computer or a calculator. That is one thing, like most people kind of, when you're asked to design those things, you kind of get confused about whether you're going to design a computer or most people end up designing a computer or a calculator. So let's know what we will be doing. So we're going to design a microprocessor, but because of how these things is like, so if you were to design a microprocessor where like you don't have access to this room, you are just designing it with these external components in mind, it becomes a little bit confusing and then a little complicated too, because actually that's what it is. A microprocessor is more complicated than a microcontroller. So microcontroller are more specific, and they are more specific. So because of that, actually we will be designing a microcontroller here in this case. So it will be more like a microcontroller because we'll have this room, this RAM, this IO. They will all be will interface then, like they will kind of, but I will try to kind of separate those two so that you can see the microprocessor part and then see the external components. So they will just be in one, somehow, something like that. We'll kind of integrate the two in one of it, so to make things easier for us, right? But still, it's going to be a microprocessor. All right, so that's just for clarity. Okay, so let's first see a quick overview of the various components. This is just going to be a quick overview. I'm not going to go into detail about any of the components. Just I expect that you should I'm sure you'll be able to read on them, and then you can read on them online and then watch some other YouTube videos. I mean, it will work. So let's see. I will talk a little about the register. Let's see first and see how the registers they are like, right? So I have a Logic open here. So by the way, the simulator I'll be using for everything here is going to be Logic. Like this is what we will use for everything. So let me first get something out of the way. So now I want us to look at this thing, right? So basically computer memory, the basic building block is going to be a latch. So this is a basic SL latch. This is a basic SL latch I have here, this schematic, right? And then other modifications as this. So if I modify and add this additional components, I get a gated SL latch or something. So you can revise your latches and then the flip-flop so they can get a clear idea of this, right? So that is a basic building block of what computer memory or something. So the latch or the latch. So It's from the latch that you get this flip-flop and all the rest. So what I want to focus on is knowing like the difference between the latch and the flip-flop. So it's quite important. So I will kind of I have some few diagram here. Let me try and get them so that I can use to explain the difference between the two. So let's take okay, so let's take a latch first and see what's the difference. So a latch and then a flip-flop, they are, yeah, the major difference lies in the triggering mode. The triggering, that is, when do they correspond, like, when do they respond to the clock or something like that. Yeah, when do they respond to the clock? So for latches, they normally, they are not edge triggered, they are either high or low. So let's say I have a active, high latch, right? So which means when the clock is high, it will correspond what to the input, like the input will, will follow, the output will follow the data line, right? So let's see, this is a timing diagram. I don't know if, but try and follow. Is so let's see, these represent, this is what the data signal, and then this is the clock signal, you see. So let's see for the latch. See, as you can see here, whenever the clock here, for instance here, this is let's see. So whenever the clock is high, you see that the Q here follow the data input. So the data is low, the clock is high, so the output is also low. Have you seen it now? And you see, so let's see all the clock. Only when the clock is high, so this is the active high latch. So only when the clock is high, whatever is is on the data line just appear there. So that's how you can see here. The clock is high between this period, and then you can see the data line. The here is high, and then it just follow what is on the data line, right? So that's how the latches work. So it could be the other way around. This could have been a active low latch, so which means it reacts when the clock is low. So with that out of the way, let's see the D flip-flop. So that was the D latch. So let's see the timing diagram for the D flip-flop. So now for the flip-flop, the major difference lies in what they are edge triggered. So it could either be on the falling edge of the clock or on the rising edge of the clock. Now what do I mean about the edge triggering? Now let's see, this is this diagram. Let's try and follow this timing diagram, right? So these are transition of the clock. Yes, square wave stuff. So these are the clock transition. Now if you notice here, right, the Q output, right, the output Q only correspond, it only follow the data input when on the rising edge of the clock. So see here at this rising edge here, at this particular, okay, let's start right at this rising edge here. See the data line was actually low, so you see the Q follow it, right? And the Q is the next rising edge of the clock at here. So at that instant the data line was high, so that's how the Q became high, as you can see, right? And the same thing just goes. So on the rising edge, whatever is on the data line will appear on the output Q, and then our other state of the clock, it will not follow, only on the rising edge of the clock. So yeah, I think that's basically how latches and then flip-flop are like.